X-rays are pretty neat. Odds are you've at least heard of them in the context of medicine since they're useful for imaging inside the human body. While visible light is reflecting off of you and ultraviolet light is busy giving you a skin tan, X-rays can pass through skin. They pass through soft tissues like muscle and fat and reflect off of denser materials such as bone, teeth, and metal. These radiographs help doctors image internal structures to make diagnoses, but you may be wondering just what exactly are these invisible miracle waves? In science class, we learned that X-rays are a type of electromagnetic radiation. Weaker types like radio and microwaves fall at one end of the electromagnetic spectrum. Visible light takes up a narrow range in the middle, and then X-rays lie at the most energetic side. We call it the electromagnetic spectrum because of the connection between light and electromagnetic fields. James Maxwell calculated in 1862 that oscillating electromagnetic fields would travel through space at the speed of light. And Heinrich Hertz would later confirm Maxwell's equations with radio wave experiments. It wasn't until November 1895 that Wilhelm Röntgen discovered X-rays while experimenting with cathode ray tubes. Cathode rays are emitted from the negatively charged electrode when a high voltage is applied across the cathode tube. While invisible to the naked eye, they can be observed by their interaction with matter, causing a fluorescent glow. This is the principle behind how neon signs work. Röntgen was testing how cathode rays could cause fluorescence in barium platinocyanide-coated cardboard outside of the tube. He darkened the room to check the opacity of this cardboard when he noticed that another barium platinocyanide screen off to the side was mysteriously glowing too. He dubbed this phenomenon X-rays, X meaning a mathematical unknown. So, what's happening here? In the late 19th century, there was debate about what exactly cathode rays are. J.J. Thomson would measure the mass of cathode rays in 1897 and found a particle 1,800 times lighter than hydrogen, the electron. In every atom, a number of electrons orbit around a nucleus. Niels Bohr proposed a model in 1913 for the structure of atoms where electrons occupy distinct orbitals. We know today that the actual electron orbitals look like clouds in accordance with the equation Erwin Schrödinger proposed in 1926. Some of these orbitals in the Heisenberg-Schrödinger model look kind of funky, so the Bohr model is still useful for visualizing atoms as a nucleus with a bunch of electrons orbiting in distinct energy levels. Each element has a ground state for its electron configuration based on its position in the periodic table. However, electrons can also be excited to higher orbitals with sufficient energy, say from an incoming beam of electrons or photons. Likewise, electrons will drop back down from excited states and release energy in the form of photons. The electrons Röntgen fired from his cathode ray tube momentarily ionized the electrons in the barium platinocyanide screen, which then promptly relaxed and released visible light. At the same time, this interaction also generated X-rays, which in turn excited electrons in the screen off to the side. So now we have means to generate X-rays, and we quickly realized we can take pictures with them. After discovering these X-rays, Röntgen began eating and sleeping in his lab, grad student at art, as he interrogated how this new phenomenon behaves. In one of his tests, he held up a piece of lead to the X-rays to see if it could block them. In this image created on the barium platinocyanide, he saw that not only did the lead reflect the X-rays, but so did the bones in his hand, inadvertently creating the first radiograph. His research and subsequent publications would get Röntgen several awards, including the first Nobel Prize in Physics. The application of X-rays for medicine was apparent and quickly adopted. Immediately after Röntgen published his findings, experimenters were playing with X-ray imaging. And in May 1896, Thomas Edison would lead the development of the first mass-produced fluoroscope, a live X-ray imager. But medical imaging was just the beginning of what X-rays would do for science. In the decade following their discovery, there was ongoing discourse about what exactly X-rays and electromagnetic radiation actually are. Albert Einstein proposed the concept of photons in 1905, which agreed with how X-rays behaved as particles losing momentum upon collision with electrons, demonstrated by Arthur Compton's observation of X-ray shift. However, there was also evidence suggesting that electromagnetic radiation is a wave, including Arnold Sommerfield's single-slit experiments, which calculated X-ray wavelengths to be around 1 angstrom. So, is light a particle or a wave? Yes. It turns out that any moving particle has some uncertainty as to its position. Quantum mechanics can be a little tricky for our monkey brains to comprehend, given how classical motion applies so well to everyday life at the macro scale. For some atomic particles and light, the uncertainty is great enough that we need to actually contend with particle-wave duality. This can be demonstrated with the double-slit experiment, where electrons or photons shot through two nearby slits will interfere with each other and create a wave-like pattern. Curiously, this interference pattern remains even when launching individual particles, and the wave-like behavior collapses to particle-like behavior if someone measures the particles at the slits. Louis de Broglie wrote about this in his 1923 paper and PhD thesis, that such particles have an internal frequency and therefore a wavelength. For everyday objects, the de Broglie wavelength is many orders of magnitude smaller than the object itself. But for subatomic particles like electrons, the wavelength is comparable to the size of atomic radii and therefore cannot be ignored. The de Broglie matter wave doesn't apply to photons because they are massless particles. However, they are still waves of oscillating electric and magnetic fields with energy and momentum. And as the energy of a photon increases, its wavelength gets smaller. To this day, science is yet to fully explain the why behind particle-wave duality, as that's more a conundrum of philosophy. However, we understand it well enough to use electrons and photons to solve practical problems in science. We now have a suite of characterization techniques that utilize some combination of electron-electron interactions, electron relaxation generating photons, and photons interacting with matter. One class of instruments using electrons themselves for characterization are electron microscopes. Similar to the cathode ray tube, electron microscopes generate electron beams in a vacuum via an electron gun, now with the added precision of electron lenses focusing the beam. Scanning electron microscopes, or SEM, work by scanning across a sample with an electron beam and measuring how many bounce off the surface. There are two main electron interactions SEM is typically used for: secondary electrons and backscatter electrons. With the secondary electron imaging mode, the microscope measures the secondary electrons, which only penetrate a few nanometers and is very sensitive to surface detail. In backscattered electron imaging, the microscope measures electrons which penetrate deeper and are more sensitive to relative composition. Elements further down the periodic table have more electrons in their clouds and scatter the incoming electron beam more and appear brighter. On top of this, the electron beam used in SEM can be used for energy dispersive X-ray spectroscopy, or EDS. Just like when Röntgen discovered electrons, the electron gun also generates X-rays from a sample. Electrons which don't scatter off a material, but instead knock an electron out from the inner shells of an atom. Just as heavier elements scatter electrons more easily, it takes more energy to penetrate their electron clouds and get X-rays. Each element emits an X-ray spectra depending on the voltage of the incoming beam and the energy levels which electrons can come from to refill the inner shell. The peaks of the spectra generated with EDS can be used to identify elements in a sample and approximate their relative abundances. The EDS data can be overlaid on top of an SEM image to determine where each element is located. We can also characterize materials by shooting X-rays at them. Just as with Röntgen's experiments, an electron beam generates X-rays from a target which are then directed towards the subject. This is the principle behind macroscale X-rays such as medical radiographs, but X-rays can also be used to look at small things with X-ray microscopy. They're not quite as powerful as electron microscopes in terms of magnification, but they don't need to put their sample in a high vacuum, and X-rays penetrate inside subjects that are opaque to visible light or electron beams. Another use of X-rays for materials characterization is crystallography. Metals, along with many ceramics and some polymers, have crystalline structures where atoms are arranged in a regularly repeating pattern called a unit cell. We can think of materials as a bunch of spheres packed together depending on their atomic bonds, the unit cell describing how the atoms are organized. Materials scientists and engineers care about crystals because they tell us about how a solid was formed as well as a material's properties. For example, steel that is cooled slowly will solidify first into austenite, a face-centered cubic phase, and then transform into bainite, a body-centered cubic crystal of iron with other phases mixed in. The carbon mixed in with the bainite will start forming grains of cementite, an iron-carbon compound, and if cooled slowly enough with the right mixture, can even form alternating layers of iron and graphite. Meanwhile, if steel is quenched rapidly, it will be primarily made of martensite, a phase that is basically the same as bainite's body-centered cubic structure, but taller with spaces for individual carbon atoms to fill. Martensite is definitively stronger than bainite, but also more brittle. Depending on what processing conditions are used, materials can be designed to have specific structures and phases to control a material's properties. So, how do X-rays tell us about crystals? Because X-rays can be generated on the scale of atomic spacings, X-ray diffraction, XRD, can be used to determine crystal structure. X-rays diffract off crystal lattices upon interacting with crystal planes and constructively interfere into distinct peaks according to Bragg's law. The diffractometer scans a material to determine which angles X-rays diffract the most. Using these peaks, we can compare the spectra to previous data to determine not just what compounds are present, but also the crystal phases and relative compositions. In this example, bainite was heated up until it transformed back into austenite, which gained a stronger diffraction peak at its 111 and 200 planes, and loses its peak from the 110 planes. X-rays have been truly instrumental to modern science. They were fundamental to the discovery of two fundamental particles of the universe, the electron and the photon. Ever since their discovery, we've been using them to study inside of things, the human body, art pieces, archaeology, your luggage. One historic use of X-ray crystallography was when Rosalind Franklin collected data in the 1950s showing DNA is a double helix. Because X-rays are intimately connected to electron activity, we can study materials, whether they're atoms here on Earth or emitted from the stars from which they came. So, that's why X-rays are pretty neat.